Well, the second question is how to look upon a circuit. First, we can divide circuits into different groups according to their loads. If the load of the circuit only consists of resistors, we call it a resistive circuit. If the circuit consists capacitors and/or inductors, then it's a dynamic circuit. For dynamic circuits, we can also divide them according to the time we are interested. If we are interested in the change of voltage and currents in the transient process of the dynamic circuits, we call it transient analysis. For example, in a circuit like this, if we know the source is a DC source, and by learning the following lectures, we can know that this is a changing trend of the voltage across the capacitor. The waveform's changing process from this point to this point is a transient analysis. Besides this, we may also be interested in the steady-state operation point. In other words, we are interested in the value before and after the changing process. It's called steady-state analysis. We just divide according to the load. We can also divide according to the source. The circuit may only contain DC sources, that is a flashing straight line on the screen. It's a DC voltage source. The source can also contain the AC source. The AC source can be a sinusoidal AC, as a waveform shown on the screen, or periodical source more generally. In PEC courses, we will introduce you the method to analyze all kinds of circuits, including the resistive circuit and the dynamic circuits with DC, sinusoidal, and periodic sources. The second question we are going to discuss is the circuit model. Let's start by the ideal circuit elements. These ideal circuit elements describing the simple relationship between voltage and current are all abstracted from real electric circuit elements. The two-terminal ideal circuit elements discussed in this course include the resistor. It's a block in Chinese standard and is a such symbol in Western textbook. We don't differentiate between them in this course. The two-terminal ideal circuit elements also include the inductor. Here's its symbol. The capacitor symbol is here. And the source. If a source is a DC one, it's often drawn like this. More generally, we may draw it like this. In the second aspect of the question, let's discuss how to establish a model. In other words, how to model the ideal electric circuit elements from the real ones. For the lighting circuit of an electric torch you've just seen, use the abstraction, we can get the model of battery, switch, bulb, and transmission line. One of the simple models is like this. We use a resistor and a voltage source connecting in series to represent a battery. We use an ideal switch to represent a real switch. We use a linear resistor to represent a bulb. We use ideal lines to represent the real connecting lines. Actually, the model is very simple. Why? The value of the resistor is constant in the model, but in fact, the resistance of the bulb will be changing with the lighting time. The inner resistance of the battery is constant in the model, but in fact, it will be changing with the power supply time. The whole resistance of the line is ignored in the model, and the line is thought to be ideal one, but in fact, it has a resistance in real, and there's also the resistance in the connection of lines and elements. So here's the problem. You must think, why not use more accurate models to model them? In the following lectures, we will discuss your problem in detail. Next, we will introduce the classification of circuits. We mainly discuss two classifications in this lesson. First is the linear and the nonlinear circuit. We take the resistors, for example. We are all familiar with them. If you mark the direction of the voltage and current like this, then we must obey the Ohm's law. Multiply R by I, we get U. Then we often use stimulation or excitation and response to describe the relationship of elements in the circuit. For example, if we think the stimulation is a voltage and the response is a current, then the relationship between the stimulation and the response is equal R times I. It's a linear relationship, and we call the linear element is the element that the relationship between its stimulation and response is linear. Now we discuss why U equals R times I is a linear relationship. It needs to be discussed in two aspects. Firstly, if the stimulation changes k times, then from the equation U equals R times I, then the response must be changed to k times U over R. It is equal to U over R times k. So the response becomes k times of the former one. Secondly, if the stimulation becomes the sum of two stimulations, then the response must become the sum of two stimulations divided by R. They are respectively U1 divided by R plus U2 divided by R. It is the sum of two responses under independent stimulations, respectively. If any relationship between stimulation and response meets such a relationship, we call it homogeneity. If it meets such a relationship, we call it additivity. The relationship satisfying homogeneity and additivity is a linear relationship. If all the loads in the circuit are linear elements, the circuit is a linear circuit. A linear circuit is described by a linear equation. You will comprehend this in the future. So what's a nonlinear circuit? As long as one or more loads have nonlinear relationship, then it is a nonlinear circuit, and it is described by a nonlinear equation. The second discussion is about a planar circuit or non-planar circuit. The so-called planar circuit means that it can be drawn on a plane, thus enables that all the elements don't intersect with each other. We take such a circuit, for example, all the elements don't intersect with each other. Now let's look at such a circuit. It seems that this element intersects with this one. In fact, we can redraw this circuit in this way to make it like this. You should pay attention to what I draw here. You see, this circuit and this one is totally same in topology. For the right circuit, there are no intersections between any two elements, so it's still a planar circuit. There must be non-planar circuit with respect to planar circuits. In other words, no matter how you redraw it, the circuit still have intersections between the elements. Take such a circuit, for example. No matter how you redraw this circuit, the elements will intersect with it, or with it, or with it, or with it. So such a circuit is a non-planar circuit. It's relatively easy to analyze planar circuits. Non-planar circuits need some special considerations. In this course, the circuit we discuss are all planar circuits. Okay, this is the end of lecture 2.